project is done under the supervision of Dr. Nasser Qaddoumi and Dr. Ayman Al-Hag. The group members are Mustafa, Assaf, Shahd, Amin, Maryam, Al-Majidi, and myself, AbdAlmonam. To begin with, I'm going to go through the outline where we will introduce the motivation and the objectives of the project. Then we'll go through the literature review, the design specifications and analysis, the estimated budget, and conclude with the achieved tasks and the future work. Power transformers are the most expensive asset in a power grid. They have a life expectancy that ranges between 20 to 35 years. As the power transformer exceeds its life expectancy, it needs to be replaced. However, since a lot of power transformers have already exceeded their life expectancy, where those transformers are already in service, it will cost the utility a lot of money to change them all at once. The proposed solution is to change those that have higher degraded insulation. To determine the level of the degraded insulation, some factors needs to be monitored, such as the partial discharge. The detected level of a partial discharge can determine whether the transformer needs to be replaced or not. Our aim in this project is to investigate the high-frequency components of the partial discharge signal within an oil-insulated power transformer. To be able to investigate the high-frequency components, we need to design a high-frequency wideband antenna that is compact and capable of detecting the partial discharge signal with high accuracy. And now I leave you with my colleague Maryam to continue the literature.
Thank you, AbdAlmonam. Now, before discussing the partial discharge detection methods, the question is, what is partial discharge? According to the IEC definition, partial discharge is a localized dielectric breakdown of a small portion of a solid or liquid electrical insulation system under high voltage stress. There are several types of partial discharge. However, we mainly considered four of them: sharp point, surface, void, and floating discharge. For the sharp point discharge, it usually occurs during the manufacturing process of the transformer, or can develop during the operation of the transformer due to mechanical distortion. The surface discharge, however, occurs in the interface between different materials when there is a high field component parallel to the dielectric surface, which will lead to the deterioration of the dielectric material and eventually to the breakdown of the transformer. Void discharge could be cracks in the solid insulation system or bubbles in the liquid insulation. Finally, the floating discharge could be due to badly earthed or floating parts in the transformer in which a defined potential does not exist. Those are simulation models for the sharp point and the surface discharge. When a partial discharge occurs in a transformer, it usually results in several macroscopic physical effects, such as light, sound, high-frequency waves, chemical effects, and heat, each of which has its own detection method. Utility companies usually use the dissolved gas analysis in order to determine the chemical properties of the insulation. It's an offline detection method which could indicate the type of the fault that occurred in the transformer through key gases. Also determines the oil degradation method. For the electrical property of the partial discharge, a high-frequency current transformer is used, which uses the magnetic coupling. However, since the PD buses, since the HFCT cannot detect PD buses with a fast rise time, it is not applicable in our project. For the sound property, the acoustic method could be used, in which acoustic signals are generated from the formation of mechanical waves due to the explosion of partial discharge in the transformer. Since the acoustic sensors are placed outside of the transformer, the signal is attenuated during propagation due to the materials within, and therefore has a low signal-to-noise ratio. And finally, the ultra-high frequency sensor, which is based on the fact that the partial discharge radiates electromagnetic waves with frequencies in the ultra-high range from 0.3 to 6 gigahertz. And since this particular type of sensor is placed inside the transformer, the signal is less attenuated than that of the acoustic method, therefore has a higher signal-to-noise ratio. In order to determine the detection method we're going to implement in our project, we listed the advantages and disadvantages of each, and we found that the UHF wideband antennas, in terms of accuracy and signal-to-noise ratio, is better than those of the other types, in addition to the low attenuation, low cost, and ease of installation, in addition to its immunity against a wide range of disturbing signals. Although the localization is limited to only new transformers, we decided with this type of detection because the other detection methods are exhausted through research. And we believe that the UHF wideband antennas are worth investigating and developing for our project. And now my colleague Shahd will continue with the design criteria for the antenna.
So after deciding to go with the ultra-high frequency partial discharge detection, now we need to decide which type of antenna we're going to use. So in order to do this, we listed a set of criteria that must be satisfied in our design antenna. The first criteria is that the lowest resonant frequency of the antenna should be around 300 MHz. This is to ensure that our PD signal is separated from the air corona discharge caused by the high voltage terminal meter transformer. The second criteria is that the frequency bandwidth of the antenna should exceed several hundreds of megahertz. This is to ensure that the PD sensitivity is high enough to detect the partial discharge. Finally, and the most important criteria is the size of the antenna. As AbdAlmonam mentioned, we are targeting the old transformer in which there are no direct windows available. So the only access point to the tank of the old transformer is the drain valve, which has an average diameter of 20 centimeters. However, it's very difficult for a regular antenna to satisfy both criteria of size and frequency at the same time. This is because as the frequency bandwidth of the antenna increases, the size has to be increased too. So after an extensive review of literature, we were able to find one antenna that shows a good performance to meet the two criteria of size and frequency at the same time. This antenna is called Hilbert fractal antenna. Hilbert fractal antenna is basically a patch or a microstrip antenna that is based upon the Hilbert fractal curve, as shown here. Hilbert fractal curve is a continuous curve with self-symmetry characteristics. It comes with order from n equal to 1 up to n equal to infinity, where it occupies the whole 2D plane. As you can see, if the order of the antenna increases, the length of the antenna will increase in the same area, and the number of according to the review of literature, the number of resonant frequency of the antenna will increase as the order increases. Also, the lowest resonant frequency will the lowest resonant frequency value will decrease. So the advantage of using Hilbert fractal antenna is that it's a low-profile antenna. It's very easy to fabricate using etching or photolithography. It's easy to feed where it matchable in the passband with a coaxial cable. It's easy to use in an array which may be the potential of future work where localization is required. And finally, its radiation pattern is hemispherical with a moderate directivity from 6 to 8 dB. So the Hilbert, as any other microstrip antenna, the Hilbert antenna consists of 3 layers. The top one is the copper conductor, in which we have our Hilbert fractal curve one. The middle one is the insulation board or the substrate. Here we choose Fi4 epoxy, and the bottom one is the copper shim or the ground. So the design of Hilbert fractal antenna depends upon 6 main factors. First is the order of the antenna, then the side dimension of the DCB, the width of the conductor, the thickness of the DCB, the dielectric constant or the type of the substrate used, and finally the feeding point and the feeding method. So for the order, the dielectric constant and the feeding method, it was concluded from the simulations that we discussed later that the optimum order is the first order in our application, and the optimum substrate is Fi4 epoxy with the dielectric constant of 4.4, and that the coaxial cable with an impedance is the optimum feeding method. With a coaxial impedance of 50 is the optimum feeding method. So back to the side dimension. For the side dimension, we started with an assumption of 10 centimeters for the overall length of the PCB. Then we used, this is according to the size criteria that I mentioned before, and then we used this value to find the width and the thickness of the PCB using a set of equations that were retrieved from installation paper.
Thank you, Shahd. Now, as my partner Shahd discussed, that we looked through lots of antenna that can suit our application, which is design an antenna that is capable of detecting a partial discharge signal. And we came to the conclusion that we're going to use the Hilbert antenna, to be specific, the fourth order Hilbert. The simulation was done in a program called HFSS, which stands for High Frequency Structure Simulation. The simulation was done on the optimum parameter, which is the length, the thickness of the PCB, and the thickness of the patch itself, which was found by equations. However, the feed point and the material was found through the simulation from different feed point and different material we're going to discuss in the next slide. First, we measured our antenna performance. As you can see, the different resonant frequency shows up different places, different frequency. Same thing applies for different material, where we tried the material that was suggested by the literature, which called Rogers RT. It showed different performance, where the first resonant frequency showed up at around 1.4 gigahertz, which is not suitable for our application, which is partial discharge detection. Now I'll leave you with my partner AbdAlmonam.
Thank you, Mustafa. Now, our proposed system for the measurement of partial discharge is composed of the oil-filled tank, where the partial discharge signal will be artificially generated inside. The antenna will be placed at the bottom of the tank to capture the signal and send it through the high-frequency amplifier through a coaxial cable. The high-frequency amplifier will feed the signal to the spectrum analyzer, where it will be digitized and sent to the computer for further processing. Our data acquisition is the high-frequency Rodian-Schwartz FSB9 that has a frequency range from 9 kHz up to 13.6 GHz. The spectrum analyzer can be interfaced with the computer through an RS-232 to a USB cable, and it's capable of sending data in real time for the purpose of signal processing. Moreover, the high-frequency amplifier has a frequency range from 0.5 to 2 GHz, gain from 29 to 35 dB, and passband flatness between plus and minus 1.4 dB. The frequency range of the proposed high-frequency amplifier counts as a phase one of the measurement system, where we will use other high-frequency amplifiers to cover more frequency ranges. The estimated budget for this design is divided into several components. However, we would only need to buy the PCBs, as the oil tank, the PD modeling circuit, and the spectrum analyzer are available in the lab. This shows our project plan for senior design 1 and 2. Our whole design system depends on the antenna, where the implementation of the antenna will help us in detecting the partial discharge for future measurement. For conclusion, the ultra-high frequency detection system proved its reliability in investigating the high frequency components of the partial discharge signal, starting from 0.3 GHz onwards. The fourth order Hilbert antenna met the desired specifications of both frequency range and size. The simulations of the Hilbert antenna showed promising results in detecting the partial discharge signal. The future work that needs to be done in senior design 2 is the building and characterizing of the antenna, and implementing the measurement system, and determining whether what we are receiving is a partial discharge signal or simple noise. The system can be improved by characterizing the partial discharge signal and finding its the type of the detected signal, and the location in 3D for the partial discharge signal can be determined within the oil-filled tank. Those are our references, and
my question: how do you install the antenna in the transformer?
Okay. In our case, we're going to use the oil-filled tank in the lab, or you can simply open the lid and put the antenna. However, in the field, in the utility, the antenna can be placed through the drain valve, where the antenna is actually smaller than the input of the drain valve.
So you open the drain valve and install the antenna. This is what you are going to do.
Basically, yeah.
In the lab. So, but you are going to lose some of the oil, right?
Some of the oil in what sense?
Like when you open the wall.
But
They do open it for DGA, for refilling or
when they want to when they want to do the DGA analysis for the oil, they take a sample from it. So a small portion would not.
Yeah, I mean the time for the installation and so.
But it wouldn't take a lot of time, so we're only going to insert it and close the valve instantly.
Okay, and this is connected to outside, right? So how do you connect it outside through the box?
Through a coaxial cable, and it will be surrounded by rubber, where it will prevent the oil from coming out while the antenna is installed.
From the same box?
Yes.
Okay. The current solutions for using antenna, how different your proposal here around the current solution using antenna for detecting partial discharge? How different your solution?
The UHF wideband antenna, it's online, and DGA is offline, so that's limited because we want it to be continuously monitored. We want the transformer to be continuously monitored. So we disregarded the DGA.
Antennas were used previously in detecting partial discharge. How is this different from what was done earlier?
Okay, in previous method of detecting partial discharge using high frequency or antenna, they were using defined antenna or regular antenna. What we were trying to do here is design our own antenna, which is capable of doing the same thing, but with a better criteria, which is the size and the bandwidth.
And we are going to detect the high frequency components